In this video, I'm going to show you how we can prove trigonometric identities that involve other functions. Here you can see a list of basic trigonometric identities that you have to be familiar with. As the first example, we want to prove that ln of secant of theta is equal negative ln of cosine theta. We need these type of identities to prove, especially for courses like calculus. So we want to prove that ln of secant of theta is equal negative ln of cosine theta. It should be clear for you that it's a good idea to replace the secant theta with 1 over cosine theta. Because, attention, in the other side that we want to get to, we have cosine theta, so it's a good idea to replace secant theta with 1 over cosine theta. So we start from the left side, ln of secant theta, and we replace the secant with 1 over cosine. 1 over cosine can be written as cosine theta to the power of negative 1. We know that we can bring the power down to the front here because this is one of the properties of logarithmic functions. So we can write this as negative ln of cosine theta. Cosine theta, not x. And this proves this identity. So we started from left side and we got to the other side. So ln of secant is negative ln of cosine. Let me show you another example. Ln of tangent plus ln of cotangent is 0. Let me remind you one of the properties of logarithmic functions. And you know that ln, or natural logarithm, is a logarithmic function. Ln of a plus ln of b is equal to ln of AB. This is one of the most important properties of logarithmic functions. So ln of tangent plus ln of cotangent can be written as ln of tangent times cotangent. And we want to prove that this is equal to 0. We know that the tangent and cotangent are reciprocal of each other. But if you don't know this, that they are reciprocal of each other, and so their product is 1, simply you can replace tangent with sine over cosine. If we remember the quotient identities, we can write tangent as sine over cosine and cotangent as cosine over sine. This is based on the quotient identities. Look at the quotient identities. Tangent is sine over cosine. Cotangent is cosine over sine. And if you know these two identities, you know that the tangent and cotangent are reciprocal of each other. Because look at this, tangent is sine over cosine, cotangent is cosine over sine. So these two are reciprocal of each other. And so their product is 1. So here, this product here in the bracket, in the absolute, this product is 1 because sine with sine, cosine with cosine cancels. We can simplify the numerator with denominator in the multiplication of fractions. So we have ln of 1. So this equals ln of absolute of 1, which is 1. And we know that logarithm of 1 or log of 1 is always 0. Ln of 1 is 0. So the answer is 0. So we prove that ln of tangent plus ln of cotangent is always 0. Now we want to prove these identities. E to the sine to the 2 times by e to the cosine to the 2 is e. This should be easy for you to prove this identity. Remember, one of the properties of exponential functions or exponential expressions basically is that if the base is the same, we can add the powers. This is one of the basic properties of expressions with powers. If the base is the same, we can add the powers. So we can write this side, the left side, in the form of e to the sine to the 2 plus cosine to the 2. Based on the Pythagorean identity, we know that sine to the 2 plus cosine to the 2 is 1. So this equals e to the 1, which is e. So we go to the other side. And this completes the proof of this identity. Now look at the next example. E to the power of x plus 2 ln of sine of x is equal to e to the x sine to the 2x. Look at the left side. It's a good idea to start from the left side because it's more complicated and gradually try to get to the other side. Here we have e to the x. In the other side also we have e to the x. So we have to do nothing about this, but we have to try to prove that e to the power of this is basically sine to the 2. But before I show you this, let me remind you a property, a relation between exponential function and logarithmic function. E to the power of ln of a is always a. You should be familiar with this relation or identity for exponential functions and logarithmic functions. The reason behind this rule is that we know that logarithmic function and exponential functions are inverse of each other. They are inverse functions. So if we combine them with each other, they cancel each other. And when they cancel each other, this goes with this. What remains? A. So e to the power of ln of a is a. The other thing that I have to mention here is that if we have a coefficient like say k, ln of a, we can bring this coefficient to the power and we can write this as ln of a to the k. This is another property of logarithmic functions, that the exponent, the power, can be moved to the front here, or if we have a coefficient we can bring it to the power. Now let us start to prove this relation here. And it's a good idea to start from the complicated part and show that this equals the other side. So we start with e to the x plus 2 ln of sine of x. This equals e to the x times e to the 2 ln of sine of x. Attention, the base is the same. If we add the top powers, we back to the original expression. Now, here we write this in the form of e to the x times e to the power of ln of. We bring this coefficient to the power of the expression. So then we have ln of sine to the 2. So we have e to the ln of sine to the 2x. If you wonder what happened to that absolute, because now this sine has a power 2, so definitely this is positive. And when something is positive, we don't need to put absolute for that. Here for sine we have absolute here. But when the power goes on top of sine, sine raises to the power of 2, and so it's not negative, so there is no need to put absolute for that. Now if we simplify this equals e to the x times y. Now with the aim of this property, e to the ln of this is equal, e to the ln of a is a, e to the ln of this is this. So we have sine to the 2x. This is equal to this. And this completes the proof of this identity. Here we want to show that if x is r cosine theta and y is r sine theta, then x to the 2 plus y to the 2 is r to the 2. If you are familiar with polar coordinates, then this relation should be clear for you, that x to the 2 plus y to the 2 is r to the 2 in the polar coordinate. But here we want to prove this relation. If x is r cosine and y is r sine theta, then x to the 2 plus y to the 2 is r to the 2. To prove this relation, we can substitute this for x and we can substitute this for y, and then we have to show that if we simplify that, it equals r to the 2. So for proof of this, we substitute x with r cosine theta, which is given, so r cosine to the 2 plus r sine theta to the 2. To simplify this, we raise each bracket to the 2, r2 cosine to the 2 plus r2 sine to the 2. The power is for both of these two, r to the 2 cosine to the 2. And same thing for the other bracket. Now, in these two terms, we have r to the 2 as a common factor. So we factor r to the 2 from these two terms, and then we have cosine to the 2 plus sine to the 2. But we know that cosine to the 2 plus sine to the 2 is always 1 from the Pythagorean identity. So the bracket is 1. And if the bracket is 1, so we have r to the 2 times by 1, which is r to the 2. So we prove that x to the 2 plus y to the 2, which is this, is always r to the 2. So let me write this here. This expression is x to the 2 plus y to the 2. This expression is x to the 2 plus y to the 2. We simplified this and we got to the r to the 2. So we prove that this relation is true. If x equals r cosine theta sine phi, y is r sine theta sine phi, and z is r cosine phi, prove that x to the 2 plus y to the 2 plus z to the 2 is r to the 2. Some of you may know that this relation between x, y, z and r, theta and phi is the relation between Cartesian coordinate and spherical coordinate. But if you don't know this, it's not really important. We want to prove that if x equals this expression, y is this and z is this, then x to the 2 plus y to the 2 plus z to the 2 is r to the 2. The method of proof of this is similar to the previous example. We have to substitute x with this, y with this expression, z with this expression, and we have to show that it equals r to the 2. So we start from the left side and we substitute x with r cosine theta sine phi to the 2. Y is r sine theta sine phi to the 2. And z is r cosine phi to the 2. If we raise the brackets to the 2, then we have r2 cosine 2 theta sine to the 2 phi, r to the 2 sine to the 2 theta sine to the 2 phi, and finally r to the 2 cosine to the 2 phi. Now if you pay attention, these two terms, if we consider these two terms as a group, we have r to the 2 sine to the 2, r to the 2 sine to the 2 as common factor between these two. That's the reason we consider these two as a group. because if you consider all of them, the only common factor is r to the 2. But if you only consider these two as a group, we can factor r to the 2 sine to the 2, r to the 2 sine to the 2 from these two. And we have a good reason for that. You will see in a moment. If we factor r to the 2 sine to the 2 phi from these two first term, from the first term we have cosine to the 2 theta, from the other term we have sine to the 2 theta, cosine to the 2 and sine to the 2. And don't forget to write the last term, which is r to the 2 cosine to the 2 phi. This bracket is 1. So we have r to the 2 sine to the 2 phi and r to the 2 cosine to the 2 phi. Now look at these two. If we factor r to the 2 from these two, then we have sine to the 2 phi plus cosine to the 2 phi. Sine to the 2 plus cosine to the 2 by the Pythagorean identity is 1. So we have r to the 2 times 1, which is r to the 2. So we prove that x to the 2 plus y to the 2 plus z to the 2 is r to the 2. This completes the proof of this relation between Cartesian coordinate and spherical coordinate. I hope by watching this video you have learned how to use basic trigonometric identities to prove relations that involve other functions. If you like this video, please subscribe to my channel and see you in the next videos.